So my name is Nura. I currently work as a research scientist at Nura, which is a startup in Berlin that focuses on safety and security of artificial intelligence. So I spend a lot of my time thinking about the problems with artificial intelligence, specifically the problems that keep us from being able to use it on safety or security critical applications. For example, autonomous driving or using artificial intelligence for medical decisions. And one problem that I'm particularly passionate about is the explainability problem. In other words, that models that we use to make decisions are not so comprehensible by us, and the decisions that they make themselves do not always come with explanations. And in recent literature, there has been an explosion of papers in the domain of explainable AI, and it's a very popular topic that I'm sure you've heard about. But explainable AI has not solved the explainability problem yet, at least not completely. And the focus of this talk will be about the explainability problem. So first, I'll talk about what is the problem and why is it worth considering. Then I'll talk about reasons why it's still an open problem. And finally, I'll talk about the future of legislation and how legislation will shape how the explainability problem is supposed to evolve. And so we'll start with talking about the problem. So what exactly is explainability? Well, as I mentioned before, we're using machine learning models that are considered black box. It's a common term used in the literature. And the idea is this: we can have input data, we can put it into a model and get a prediction as an output. And we don't necessarily know how the model arrives at its decisions. And so one can say, okay, but why do we really care? If it's, for example, a model that classifies cats from dogs, is it so important that we know how it works? Well, we don't always need to know, but when it's making decisions that are critical, so for instance, if you input your CV into a model and it outputs a prediction that you are not a suitable candidate for this job, you will want an explanation. And the crux of the explainability problem, I believe, is that as a result, there is a lack of trust in artificial intelligence. And if we want to really reach the full potential of artificial intelligence, we have to be able to trust its decisions. And so let's look at this data scientist. He says, I have a solution. Here it shows that we are optimizing for predictive accuracy. We've developed these black box models in response to our need for highly accurate large-scale models. Why don't we just change the objective function? We can penalize it and say, no, we only want to use models that are simpler, that come with an explanation. And he has a good idea. However, we found that in general, there is a trade-off between explainability and accuracy that we can get. And now I want to say this comes with caveats. This diagram is quite popular, but it's not always the case. So for instance, linear models and decision trees are considered to be transparent or explainable because by design, we know how they work. For instance, decision trees partition the feature space, so we can know for a particular prediction exactly how it arrived at its result. On the other hand, we have ensembles, which is just a collection of models that vote, and we have deep neural networks. And these models tend to have very high predictive accuracy on complex tasks, such as image classification, but by their design, they are not always explainable. And indeed, there are cases where linear models are not explainable. So for example, if you heavily transform your features and you get regression coefficients on those transformed features, they might not be so directly explainable. And also, sometimes linear models are as accurate as neural networks in some applications. But in general, we do have to sacrifice explainability when we get predictive accuracy at a large scale. And so our data scientist has returned and he says, but okay, that's not so good. But why does my model even need to be explainable? Because I trust it. And that's good. In many cases, we can trust our models, but still want an explanation. And while there's a lot written here, I'll just give the basics. So we can explain to justify a decision. In the previous example, if your CV is rejected, you will want a justification for that. We can explain to control. So if our model is faulty on certain decisions, we can see an explanation and see how we can fix the model. And we can even explain to discover new associations. And this is quite an interesting idea that explanations teach us what we haven't been able to see ourselves in a large data setting. However, I think that this quote summarizes really what is the demand for interpretability, which is the demand for interpretability arises when there is a mismatch between the formal objectives of supervised learning and the real-world costs in a deployment setting. And I'll give some concrete examples of when we want explanation. So here's a really fascinating example about medical discovery. Some scientists at UC San Francisco have built a model that will predict whether a patient will cost a lot or not a lot, or even predict close to the actual cost that a patient will have, just from chest x-rays. And that's extremely useful, but what is it about this x-ray that will make a patient expensive? If we use what is shown below in red, a saliency map or a heat map, the red areas correspond to the parts of the image that are most instructive to the model. We can say, maybe these expensive patients have this red area in the top left corner. Let's investigate that and see what kind of associations we can learn. Another reason for explainability is adversarial settings. And this is not talked about as much, but at NeuroCat, we really focus a lot on adversarial security. So deep neural networks have another flaw in that they are deeply, they're perceptible to small shifts in the inputs. They're very fragile, actually. So I'll give an example. We look on the bottom that there are two images of a panda bear. Now, we as humans see them as panda bears. It looks like the same image. In fact, the image on the right has been perturbed very slightly in a specific manner, such that a classifier that will classify this as a panda, the image on the left, will classify the image on the right as a gibbon, which is a different animal. And we say, okay, so what? There's a mistake. We don't see this as a panda. Well, okay, but what about in the settings of autonomous vehicles? Let's look at this stop sign. What if somebody puts this reflective sticker on a stop sign? As a human being driving on the road, maybe we don't notice it because we still recognize the stop sign. Maybe a self-driving car will not. And one can imagine what kind of catastrophe can happen if a self-driving car makes a mistake when a passenger is present. And so explainability comes into play here because we can check whether a model is behaving in line with its concept, if it's conceptually sound. Is the self-driving car recognizing traffic signs for the right reasons, or is it relying rather on spurious correlations? And if we know that, then we can see how we can make our model more robust. So indeed, explainability has its reasons beyond just trusting the model. It can also save lives. And so now that we've talked quite a lot about the need for explainability, let's see what solutions we have. So as I mentioned before, there is a plethora of methods that we can use. Some methods are very specific to certain problems, some methods are more general. And for the remainder of the talk, I would like to focus on methods that are post hoc, meaning that you've already trained the model and you want to get an explanation from this trained model. And they tend to be model agnostic as well. So it's also good to focus on methods that are off the shelf. So if you have a model, you want to get an explanation. And these are the most popular methods at the moment. And so our data scientist comes back for a final time. And he says, okay, great. I know about this post hoc explanation method called line. And I have a model. Can I not just apply line to my model, get out some explanations, and call it a day? No, he cannot. Or not in every case, at least. Because there are some problems with explainable AI. And in this part, I'd like to talk about the open problems that are remaining in explainability and why explainability has not been completely solved by these explainable AI methods. And as a caveat, there are certain methods that have been created for very specific problems that do a good job. But the general methods, and typically the post hoc methods, that people tend to trust and rely on without thinking too much beforehand can be problematic. And I'll give some examples. So one problem that we have is there's a gap in interpretation, so the interpretability gap, meaning that we can get an explanation using an off-the-shelf method such as a saliency map here, but a human being still has to decide what does it mean. So for instance, here from a paper we have a convolutional neural network that takes as input chest x-rays and predicts whether the person has pneumonia. And here, this particular X-ray is predicted with 85% confidence that they have pneumonia. And along with the prediction comes an explanation in the form of a saliency map. And as in before, the red areas indicate areas that contributed the most to the model's decision. Okay, now we can show this saliency map to a radiologist or to another medical practitioner. And they say, well, this could mean several things. Maybe it's about the heart shape, maybe it's about the pulmonary artery, or maybe there was even an issue with the X-ray. Maybe there was some noise in it and it actually is not correct. The point is that we still need a radiologist to interpret this. And so we say, maybe the saliency map isn't fulfilling its promise. It's not providing an explanation that we can act on. And of course, this depends on how we define our objective. What kind of explanation do we really want? For whom? By whom? So the gap that we have is that we still need human beings to provide some interpretations. And while in some cases, such as radiology, we have radiologists, let's consider AutoML. In the future, perhaps we have completely automated systems where we start with raw data and we get out prediction and explanation, and it goes in the hands of a patient. The patient needs to be able to see and directly understand what actions to take from explanations. And when there's a gap, this ambiguity can cause some problems. And another problem that comes with explainability is this evaluation problem. So we need to actually be able to know how explainable is an explainer, which sounds a bit strange to say, especially given that explainability is not a quantitative subject, really. It's more qualitative. We do need to be able to measure it. And as I will talk about a little bit later, this has a lot to do with legislation. Because if we demand interpretability and we want to claim that our model is interpretable, we're going to have to be able to measure how interpretable it is. The problem that we have now is that there's no standard way of doing it. And there are several papers that propose metrics, and there are individual papers that have come up with explainability methods and have done user surveys. So it's not that we aren't measuring it at all, it's just that there needs to be some sort of standard metric for comparison. How do we know if SHAP is more explainable than Lyme in this particular case? And these are two examples of explainability methods. And so here's an idea, is that we can have this black box model from our previous slide. It gives us a prediction and an explanation. But then we have to think of this target persona. So we have different people who need an explanation. So a doctor, a patient, a business stakeholder who needs to be convinced that investing in this model is worth it. And so we need to be able to evaluate the opinions of all of these people with user studies and say, okay, how well do you understand? What do you understand from this explanation? What actions do you want to take? And with these results, we can then improve our explanation method for the specific problem. And so the problem is we're just not there yet. And once we establish standard metrics for measuring explainability, then we can more easily choose an explanation method for a certain problem, or it can help us come up with new methods that are more in line with the problem. And finally, a problem that we really need to discuss is the disagreement problem. In other words, that state-of-the-art post hoc explanation methods have been found to disagree in terms of explanations they output on the same prediction. And so I give an example from a paper from Krishna et al. In 2022, so this is very recent. And so the authors use the COMPASS algorithm, which is an algorithm that is predicting recidivism, or whether a person who has previously committed a crime will commit another crime. And this algorithm has come under quite a bit of scrutiny in terms of its fairness, especially towards minorities. And so if you're using an algorithm to decide whether a person will go back to prison, this can impact how a judge decides the sentence. And so this is extremely sensitive. And so in this case, it goes without saying that we need some explanation if a defendant is predicted to be someone who would return to prison. This is something fair. This is something that a person has right to. And so the authors look at the COMPASS data set, which has 7 features here, and they plot feature importances from the model using different explainers. So feature importance plot just shows to what degree has a feature contributed to the decision. So this is one from an individual decision. Suppose we have an individual who is predicted to be likely to return to prison. And a judge thinks, okay, maybe I will want to put a harsher sentence on this person. Then we want to know why. And on the left, we have LIME, which is a method of post hoc explanation, and we have kernel SHAP, which is just another state-of-the-art method. And we find that there's disagreement. So on top, we have the person's age. LIME says that age has a large contribution to the decision in a positive direction. But kernel SHAP says, no, actually, it's not a large contribution, and it's in the negative direction. And then if we look at the bottom, there is the candidate's race, where LIME says that race contributes to a small degree, but kernel SHAP says it's to a larger degree. And now, the question is, which one do we listen to? Because both are telling us conflicting things, especially on the topic of race, because if race is a significant contributor, then we question the fairness of this algorithm on this individual. The problem is that we have to ask data scientists, what do they do? So if you're a data scientist and you encounter disagreement, what are you going to do? And the authors actually conducted some user studies. And they asked questions such as this one, which is, okay, given that you find that these disagree, which one will you choose? And they asked these kind of questions to users, and they found that around 86% of users said that when they encounter the disagreement problem, they either don't know what to do with it, or they choose an arbitrary method. So maybe I will choose LIME just because I know how it works, or I've used it before, or I just like it better. And so in the large scale, maybe when you're a data scientist looking at metrics for an entire data set, maybe at the moment you don't think it's such a critical decision, but then when you look at one individual, the decision of the explainer will determine the reasons for why this person is predicted to have likelihood of committing a crime. For that one individual, it matters greatly. And so this quote says it quite well, that you could have many explanations for what a complex model is doing. Do you just pick the one that you want to be correct? Because indeed, human bias also has to do with this. And the problem is, at the moment, it seems that this is the solution that we have. And of course, again, literature is responding to the disagreement problem. It's identifying it in other domains. For instance, another paper recently identified it in education, but there's still no standard rule for what to do about this. And this has a lot to do with establishing explainability standards. So now we go to the more legal side of things. So in the near future, the European Union is expected to release the Artificial Intelligence Act, which is a set of laws that have the goal of regulating the development of artificial intelligence applications in a way such that there will be increased trust in its adoption. And something to be clear about this. First of all, that it's not yet the law of the land, so it's still being created. And if you were to go to the website of this EU AI Act, they are providing a lot of information, also quite a lot of information about where there's weakness in the current legislation, at least the proposed legislation. And their goal is not to ban artificial intelligence. In fact, regulation is always a bit controversial for the tech industry, but the EU doesn't want to say no more artificial intelligence, but they want to make sure that it's trustworthy. And what they do is they divide applications into risk categories. So some risks are unacceptable. Other risks are just high risk. So for example, this CV screening model, this would be high risk because its output decides whether or not you get an interview for a job. And then all the other applications are considered other, and they're actually going to be left less regulated. So it's not going to be an extremely strict act, except for the high security, high safety applications. And so then what is the EU AI Act going to say about explainability? This could change, but from Article 13, we can get the following information. So first, that it's going to be quantifiable, in that it has to be high-risk AI systems shall be designed and developed in a way to ensure that their operation is sufficiently transparent. So sufficiently transparent means there has to be some measure of transparency, and explainability metrics can provide that. Next, it's to enable users to interpret the system's output and use it appropriately. So user empowering. And going back to the example of the saliency map and the radiologist having to use it, an explanation has to be enabling the user to use the results of this model and make decisions. Finally, it's supposed to be compliance-oriented, in that in the future, we can envision that there's going to be some rules about your AI system has to comply with, and explainability is going to be key to ensuring compliance. Because if you have a model that is explainable to a certain degree, that can prove that you are compliant with the law. And so here are some final thoughts about this. First of all, as regulation is going to happen, we can see that explanation is going to be necessary. We have to think about the problem from now. And I've collected a few opinions because there are several differing opinions, and I want to share them with you. So first, let us insist that we do not use black box machine learning models for high-stakes decisions unless no interpretable model can be constructed that achieves the same level of accuracy. It is possible that an interpretable model can always be constructed, we just have not been trying. Perhaps if we did, we would never use black boxes for these high-stakes decisions at all. And this is from Cynthia Rudin and Joanna Radin. So I had previously quoted Cynthia Rudin. So this is one opinion. Do away with black boxes. We're not trying hard enough. We've come up with explainable models in the past. You can look at the field of statistics for this. We are relying on these models because we are lazy, and instead we should just change how we build models. That's one opinion. Now, is it applicable to everything? That's a question. People have agreements or disagreements on this, but one way of looking at explainability is that we're building the models wrong. And now let's look at the opinion of someone else who's a doctor, and he's speaking from the field of medicine. And he says, his name is Anthony Cheng, he says, instead of requiring local explanations from a complicated AI system, we should advocate for thorough and rigorous validation of these systems across as many diverse and distinct populations as possible, showing that patient and healthcare outcomes are improved and that marginalized groups are not disproportionately affected by any given system. So his concern is fairness, that in medicine, in healthcare, we want to ensure that algorithms are fair, meaning that they perform as accurately on groups of concern or across different groups of concern. So an example would be a predictive algorithm for whether a patient has pneumonia works equally well for women as it does for men. And currently, some algorithms are not performing equally across these groups. And so with this opinion, the idea is that local explanations are not going to solve the problem exactly. Rather, we need to collect better data. And we need to validate our model across these different data sets. And so the opinion of Dr. Anthony Cheng is not that explanation is necessary, it's that the data is the problem. So first, we have computer scientists who believe that the models are the problem, we shouldn't use black boxes. Next, we have someone who says, well, explainability, local explanations, they're not going to really solve the problem, and black box models shouldn't be done away with. It's rather that we need to use better data, and if we use the right data, black box models are going to perform fairly, and they will give us high utility. And now we come at a final opinion, which is the issue of explainability is really centered on the trust, not only of artificial intelligence tools, but also on those clinicians and data scientists who espouse and advocate the use of these tools. Perhaps we will all settle eventually in the diminutive sweet spot between interpretability and accuracy versus explainability, and a new paradigm of what is trustworthy and acceptable will be introduced with sufficient alignment, validation, and equity. And this is from a paper called The False Hope of Current Approaches to Explainable Artificial Intelligence in Healthcare. So the title does say a bit about the opinion of the authors, but indeed this is a very interesting quote because the authors do not say that it's about the model. They don't say it's about the data. They say it's about how we trust them. And that perhaps in the future there's going to be a new way of trusting. And it's interesting to look at this because consider current use of mobile phones or social media. One can say that the younger generation that's born with these tools is a lot more trusting than older generations that know life without these tools. And perhaps the future generations that are born with artificial intelligence being used in high security applications might never question whether they can trust it, or they just have a different way of trusting it. That we can have a future where, for instance, we have the output of algorithms and a radiologist interpreting it, and we have a combination of artificial intelligence with explanations and a human being. Or we provide different kind of explanations so that the user can choose the one that they understand the most. But we can decide ourselves what do we trust and what expectations do we have. So again, 3 different opinions. There's the models, there's the data, and then there's us. How do we trust it and what kind of systems do we build? How do we work with artificial intelligence such that we combine the best of both worlds, the computational efficiency and predictive ability of artificial intelligence, and also the human touch and human intuition and experience. And so I'd like to conclude with just this, that if there's anything that can be taken away from this talk, it's that explainability is very much an open problem. And perhaps for many of you this is obvious, but when we look at the popularity of off-the-shelf explainers, we look at how easy it is in a few lines of code to take a model that you've trained, get an explanation out of it, and then call your model explainable. It seems that there is a belief that explainability is solved by popular explainable AI methods. And it's not. And indeed, currently, there's an opportunity to solve this problem. If you have an application that's going to be deployed in high security domain, or even if it's not a high security domain, if you want to have users trust your application, then now is the time to focus on explainability and invest in coming up with a solution that works for your domain. And solving this problem is a necessary step towards realizing the goal of safe and trustworthy artificial intelligence. Thank you, and I'll take your questions.
Hi, thank you very much. Very interesting talk. So I have a question which relates to the example with classifying the X-ray picture. And basically, so when you told this, I was thinking how actually the doctor is kind of doing the same thing. And the doctor usually, I guess, would take into account like many other aspects and like what is the medical history of the patient and build some sort of mental model of like what is actually happening in the body. And so I was thinking, maybe you have come across any ways or approaches building the models in such a way that it somehow reflects the reality a bit more, and then explainability is kind of baked into it in such a way that people can reason about it. So it's not just a function that maps one data to a label, but somehow it's like a more broad and concrete reflection of reality or something like this. Have you come across any kind of these approaches in this area?
So, very good question. So, indeed, I cannot come up with specific publications off the top of my head, but I have, of course, encountered approaches towards explainability that's either an intrinsic part of the model or different kind of explanation methods besides saliency maps that provide a more well-rounded explanation to doctors and to patients, and indeed that try to mimic the way a radiologist who has been trained for years would provide an explanation or would make a decision. So this example is quite particular to this paper and quite particular to saliency maps. So indeed there has been and currently is movement in this direction. Of course, sometimes there is a cost of predictive accuracy that comes with this, but indeed people are working on it. So I'm not claiming that this is the only way that interpretations come about. It's just that this is the way that's most accessible to people. And it's much easier to just apply a saliency map than to invest in coming up with a specific solution. And so I use this example just to show that the off-the-shelf explainers that we have right now have this gap. But indeed, if you are a medical practitioner, if you're a researcher that really wants to come up with the right solution, then they will have to come up with a specific explainability method, either intrinsically in the model or post hoc, or even a combination that will more reflect how the decision is being made. But this is very difficult, so that's the challenge.
Hello, can you hear me?
Yes.
Thank you very much. I agree. It was very, very interesting, high quality overview. I feel like there is a stress point between, especially in legislation, between being realistic and kind of having the highest possible standards. You know, this being exponential technology, moving fast, it kind of requires something different, I think, from other fields. So just as a pretext to the question, I work with Dr. Robin Yampolsky. He works in AI safety and security, and he has papers on uninterpretability, unexplainability, things like that. One of his theses are about how, just like how it's hard for a human to explain to a squirrel nuclear fusion, the gap is too large, and that there are things that supremely advanced AI will simply not be able to explain to us because we won't have maybe the capacity to do it. I would say in that vein, do you agree with this line of thinking? Do we have to sort of surrender to the higher level of intelligence that it will provide and just be okay with a more general, incomplete explanation? This is a more long-term question, but just how do you view the horizon of explainability of AI, if that makes sense?
Yes, it makes sense. It's a very big question that you're asking, and thank you for asking it. So, indeed, as you said, the interpretability gap is very large in some applications, and there are even some people who argue that, for example, if you ask me, why did you come here? I don't always have a logical explanation for everything that I do, and there are multiple explanations. Or even better, ask a kid, why did you take your sister's toy? The kid is not going to give you logical step-by-step reasons. There's just, sometimes the human brain doesn't even have explanations for what we do. And some people argue, look at these examples. Humans can't explain themselves so rationally. Why do we care that artificial intelligence does? And indeed, there's another argument that the utility of these very advanced systems will be so great that maybe we will have to sacrifice some explainability and, as you say, surrender to it. So my opinion on this, I think I can't have a general opinion because it's so application specific. I mean, will you be willing to surrender to the almighty reasoning of a self-driving car? If it's the only way to get from A to B, maybe you will. Or maybe you won't if you're an experienced driver who says, no, I trust myself much more. So I would say that this is quite a big question, and my answer would just be that it really, really depends a lot on the domain, and then depends on the user. So I don't really have a concrete answer. I think with time, going back to the last quote that I shared about the new paradigm of trust, perhaps that will be part of it. Once we have a new paradigm of trust, the next generation maybe will answer this. We'll see to what degree will people in general be willing to accept the high performance of artificial intelligence without fully understanding it. And then the rest is just very personal opinions, depending on the person, depending on the application. And another thing is that trust is a very individual thing. And so if it's down to trust, then this is something that each of us will have to answer. And legislation will somehow have to come up with an answer as well. I'm not from this domain, so I don't envy these people who have to do it. Yeah.
Thank you for the presentation. So my question is twofold. First, some of these XAI techniques, like the shadow one, are very difficult even for the machine learning engineer to understand the inner workings of it. So it kind of sounds counterintuitive that those techniques provide an explanation. And a user or non-expert that does not know machine learning, it would be much harder for them to understand even like how the shared values work. How would you address this, the counterintuitive part of it? And the next question is the feature importance. Why is that considered an XAI technique? Like the regression model does provide an explanation, the relationship between the input features and the target, but that's not considered an XAI or explanation. So why do you think the XAI community is embracing this feature importance explanation? Thank you.
Okay, so thank you for the questions. Those are really good questions, and it will take some time to answer. So the first part, if I recall correctly, so the first part is that, okay, these methods such as SHAP, so there's Shapley values by their definition, but then there's Shapley additive explanations, there's kernel SHAP, there's many variations of this, and that many machine learning practitioners might not know exactly the mathematical definitions and not be able to really understand how you get these Shapley values, but you can implement it in a few lines of code. And so there is a paradox that even the people who are supposed to understand how these methods work can use them without understanding. And then we use those to explain to people who are maybe less involved with the model and might not understand. So 2 things. So first, there is the actual mechanism for how we get an explanation, and then there is the output, which is the explanation itself. So for instance, the method of SHAP, or Shapley values, this is something that will require some reading to understand. I do believe I would be quite concerned if data scientists are not able to learn how it works, because I think we should focus on methods that do have some mathematical foundation, and Shapley values do, at least in game theory, economics, mathematics. So maybe focusing on developing methods that are grounded in mathematics is a first step. And the explanation itself, though, doesn't involve as much mathematics. So we can use Shapley values to get out feature importance. And so the explanation itself, it tends to be something simpler. And indeed, it does have to come with some text, and we do have to teach human beings how to read the charts. So it's correct that there is no magic bullet that we just get an explanation that is instantly comprehensible by everyone, and that the methods that we use to get these explanations are all so simple that every data scientist who is not a mathematician necessarily will understand it. Yeah, it's not the case, indeed. And what I would do to address it is, first of all, focus on developing methods that have mathematical foundation, and second, focus on getting explanations that are in its simplest form. And that goes back to getting user studies and really learning from different kind of users how they see these explanations and in what format is most useful. And one interesting paper that I read recently proposed a surrogate model. So this is one kind of explanation, but the outputs of that, specifically for the domain of insurance, are in the form of an Excel table that will provide in numbers and words such that people working in financial industries can very easily understand this and even export it to Excel, which is a very popular tool that they use. So it would be focusing on making sure that the method is understandable by the data scientist and that the output is understandable by the specific domain by conducting user studies. So that's the first question. And so the second question, I have to recall what exactly it was about. Why? Yeah, that's also a very good, that's a good question. So why feature importance? Because as you correctly state, with linear regression models, we get the weights of the coefficients that it assigns to the features. And that is, in a way, already interpretable. And so why is that suddenly a new XAI method? Well, I would argue that linear models are in fact considered by the XAI community as a way to explain. So oftentimes you would fit a local linear model and then use those coefficients to get an explanation. So it's just a tool, it's a method, but I think a reason why it's very nice is that linear models have a beautiful mathematical definition and foundation, quite easy to understand. And why the focus on feature importance? I think that it has been found to be quite intuitive for an end user. That if you see these bar charts, for instance here, a user can know that something that's red contributes negative, something blue contributes positive, and that magnitude the size of the bar would have to do with the magnitude. And so this is something perhaps that's even coming from our elementary school education in mathematics and statistics. So I think the reason why we focus a lot on feature importance, even though it's not always accurate, as you see, there's a disagreement already with 2 methods. It's just something that's easily understood by people. And so a really good point is that we're sacrificing some of the accuracy of the explanations so that people can understand them in a way that we have been taught to understand charts from our education. And that's another thing to think about, is don't rely so much on something that's so easily explainable. But then on the other hand, if it's not easily understood by people, then what's the purpose? So very good questions that you bring up, and unfortunately no clear answers to either of them.
Any other questions?